Melbourne.
Hi, thanks for the privilege of being to talk at such a multidisciplinary conference. So I'm coming from theoretical physics and neuroscience, very much theory-oriented, and I actually don't use any experimental data yet, so I'm going to give you the other perspective. I guess in a conference like this, I kind of imagine it as a bit of a multidisciplinary tri-alogue, where we're trying to create a space where we can talk about epilepsy coming from three different places. So you've got kind of the neurologists and the epileptologists, and the electrophysiologists and the neuroscientists. Then you've got the mathematicians and the physicists and the engineers. And I want to concentrate on this area here and give you this perspective, because we do conceptualise this problem quite differently to the other two blobs. And you can see I've put in this little pretend corner here to try and define it. And I guess one of the roles of models for me is to sharpen the questions. So how does a physicist conceptualise epilepsy? And I guess the aim of this tutorial is to, one, impart some background concepts that show how we use mathematical models to describe the transitions to seizure. In order to do this, I'll give you a very brief background in neural field theory and apply this to epilepsy. And then I'll talk about, in the last third of the talk, some of the work we've been doing here at Melbourne on the role of synaptic mechanisms on the seizure transitions. So I apologise to my fellow modellers. Probably the first two-thirds of this talk will be familiar material. So the structure of the talk will be as follows. First, I'll motivate the idea of brain dynamics and some of the theoretical methods that we use to describe it and where they come from. And then I'll formally introduce a family of neural field models, which I'll unpack from this kind of canonical formalism of a few of the other models. And then I'll talk about ways of describing this transition to seizure using bifurcation theory, which Bill just mentioned. And then this part here will be the research that we've been doing at Melbourne University. This will be fairly mathematically dense and probably more directed at the modellers. And then I'll sum up and talk about the future directions. So the brain has multiple spatial and temporal scales, from genetics to molecules to single neurons in the microscale and larger networks in the mesoscale. And of course we go to regions and lobes and whole brain. So where do we begin to model epilepsy? And I guess the best place to start is probably the EEG, because that's what we measure and diagnose epilepsy by. And that's usually created by these larger networks. So we look at the mesoscale, and that's where neural field models are directed. And where do the methods or these theoretical models come from? So the idea of theoretical neuroscience or computational neuroscience, mathematical neuroscience, they're all under the same banner. Most of the sciences have a distinct theoretical component and an experimental component, and it's the iteration between these two approaches that really progresses science. So physics has it, chemistry has it, earth sciences, engineering, but not so much biology. This is still fairly new in biology and neuroscience, where the majority of the work is experimental. And having a theoretical framework actually gives us it's a framework to interpret the data and give meaning to it. And in this approach of neural modelling, we really have a dual-layered structure-function relationship. So we have the usual structure-function relationship, where we're talking about relating anatomical structure to physiological function, for example, network connectivity to network dynamics. We also have a second layer in mathematics, which is when we talk about mathematical structure and mathematical function and how the mathematical structure changes. So we think along this particular relationship on two layers. I'll be coming back to this theme a few times. So what are the goals of the theory? So of course it's, as Bill said, to generate a hypothesis that can be experimentally validated, i.e. theories that explain data and phenomena. But there's also another goal as well, and that is to actually develop the methods that generate these hypotheses. I mean, mathematically modelling the brain was no mean feat. Calculus, quantum mechanics, these theoretical approaches took centuries to develop, whereas this is a relatively young discipline here for such a complex system too. So we're in the midst of developing these methods. So some of the research, which is purely theoretical, like the work I'm going to present is about developing methods that can describe the brain and link it clearly to the physiology and the anatomy. So where do these theoretical methods come from? Most of them come from statistical physics approaches, and these developed from 19th century thermodynamics. So in the 19th century, people started writing down equations where you had the microscopic variable on one side of the equation and the macroscopic variable on the other side of the equation, linking the scales, which is probably the biggest problem in neurodynamics, is to link the scales. So if I wanted to measure the temperature of this room, I wouldn't go ahead and measure the kinetic energy of every single molecule in the room, which is the definition of temperature. I would take a bulk measurement or an average, and that's what you would see on the thermometer. Similar to, we're not going to be able to measure the output of every single neuron. We take a bulk measurement like the EEG, and that's kind of the approach that we're taking. Obviously, it's not as simple as this. You know, when we talk about electrons, particles, atoms, these are all identical. I mean, the famous physicist Steve Weinberg said, you've seen one electron, you've seen them all. And this is clearly not the case with neurons and cells and genes. So the real trick is what features can we leave in and what features can we leave out as we ascend scales. So the other thing that happens is we've got neurons which are discrete elements here, and we treat them as a field, a continuum approximation. How does that happen? So the typical approach you find in papers is to replace this whole network with the average, but there is a more detailed concept behind that. What you can do is you unfold the cortical surface or the structure into a two-dimensional lattice. And then to go from discrete to continuous, you have to take two limits in physics. The first is a thermodynamic limit, where if n is the number of neurons, you let this number go to infinity and you spread the shit out, but you keep the density of the neurons finite and constant. But this is still not a field yet. So the second limit you have to take is the continuum limit, where you let the spacing between the neurons go to zero and you treat them as true mathematical points, so that each point in the field then can become a vector or a scalar, as is the case in neurofield models, where each point represents, say, the firing rate. Then you can take a mean field of that, if you like, and you can actually leave out the spatial structure and just treat it temporally, and you get what's called a neural mass model. So it has no spatial structure, for example, for Rees-Wendling's models. That's the distinction between neural mass and field. So just to sum up, we have a continuum or mean field approach on the mesoscopic scale. We look at bulk properties, which are averages of neuronal populations, for example, the firing rate and the average membrane potentials. And these models are typically phenomenological, they're top-down. They're low-dimensional, so we can work with them mathematically. They're biophysically motivated, so we want to base them on data as much as is currently available. And the neural population, according to Freeman, is viewed as the macroscopic element for the organisation of behaviour. And these have been used pretty successfully to describe a lot of neural phenomena. Brain rhythms, epilepsy, Parkinson's, sleep dynamics, drug responses networks, dynamics, often from the same model, so they're quite versatile. So pictorially, what we do is we take this cross-section of sulci and gyri and pick a little patch here, which then shows the various laminae and the various populations within the laminae. And then we represent these populations whilst preserving the network connectivity between them. That's kind of the approach of a neural mass or neural field. So now that we've introduced brain dynamics and some of the theoretical methods in the background where they come from, I just want to then formalise this mathematically. So there will be equations, brace yourself. I want to unpack from a canonical formulation the different types of models and what differentiates them. So if we're a population of neurons, this is representing the model, this cortical field, we're taking in all of this presynaptic input over space and over time. So this is a firing rate function in the form of a sigmoid. And then we output, as a model, or as a population, the change in membrane potential. This is essentially what the model does as far as input and output goes. So I kind of want you to think of this mathematical machinery as an experimental setup, where instead of just changing a parameter, you're kind of tweaking the experiment. That's the thought experiment that we're after. And now I want to formalise this. So the first equation I'm going to put up is the most general form of a neural field model. The input's always here on the right-hand side, usually in these differential equations. So this is the firing rate that comes in. There's a delay there over time and over space. This is modelled phenomenologically from Walter Freeman in the late 70s. This has been fitted to data as the incoming firing rate. Then it gets integrated over time. Again, these distributions are based on experimental data, where you can see the current dropping off exponentially, and then we integrate it over space. This is a histogram from Batenberg and Schutz showing the exponential distribution of connectivity between populations. And what we can do now is our state variables here, the membrane potential and the firing rate, they're both over space and time, is this represents a family of neural models that's differentiated by the different temporal distributions and the different spatial distributions, so we can kind of unpack all the other models from here now. So again, with a neural mass model, we get rid of this integral here over space. It's just over time. We just treat it temporally. One of the confusing things when I was first encountering neural field theory is that this can be written in many different forms that are equivalent. So if we take a neural mass model and just look at the temporal dynamics, and we have the formalisation of that rise and decay time of the PSP, so this is over the membrane time constant and the synaptic time constant here, we can write it as an integral convolution kernel. So here's your temporal distribution, and this is your incoming firing rate with synaptic gain there. We can also write this same dynamical system as a differential operator, where here are your time constants, it's operating on the membrane potential, and here's your input incoming firing rates in synaptic gains. And then we can also write this again as a pair of coupled first-order ordinary differential equations, where this is your typical RC circuit style Hodgkin-Huxley equations, where you've got the membrane model as a leaking integrator. Here's your leaking current, and this is your synaptic current, which is then modelled as a decaying exponential. And these are all equivalent. These are all exactly the same. We can rewrite these, and this is confusing when you look in the literature. Then what we can do now that we have our canonical kind of formulations, we can add extra populations, and we can add time delays, and we can add noise. And these are often how these models generate time series that correlate to those clinically observed EEG patterns. So, for example, the Lally model. This is not a epilepsy, but a neural field model. This is roughly a macro column called a K2 set in Freeman notation. You have an excitatory population and an inhibitory population with self-connections, feedback, and they're connected to each other. Another example is the Wendling model. So this is where you have two different populations of excitatory neurons and two different populations, slow and fast, of interneurons. And then you have, for example, the Robinson model as well, where you have a thalamocortical model. So this is the cortex with self-connections and two nuclei of the thalamus, the reticular and the relay nuclei. And you have a time delay from the cortex to the thalamus. So these all have different characteristics depending on what you wish to model. So now I've briefly introduced the family of neural field models. I want to talk about how we actually model the transition to seizure and how we conceptualise this. So often we would analogize this with a phase transition. Everybody knows that how a solid turns into a liquid, turns into a gas. We get this change in the collective state of the overall behaviour, and all the molecules act in unison. And typically it's described what's called a phase diagram. So here's temperature versus pressure, showing the various phases of water and the triple point here. And ideally, as a modeller, what I would like to do is be able to draw a patient-specific phase diagram with, say, something like cortical excitability, maybe some statistic of the network connectivity, and then label these regions simple partial or secondary generalised, or have an epileptogenic zone inclusive of these ictal zones, for example. So how can we represent these changes of phase in a dynamical system? So, well, the first way everyone knows is to generate a time series. So this shows how the membrane potential changes with time, which we typically say is proportional to the EEG. This is a fairly clean signal without noise, so it's deterministic and oscillatory. And what we can do is we can represent this signal in what's called phase space. So phase space is the space of all possible trajectories of the system. So here we have two state variables plotted against each other, the firing rate and the membrane potential. You can see it starts from an initial condition, and this trajectory here is actually time as the system evolves into a stable circle. Now this circle, or torus, actually represents oscillatory activity. So if I get a pendulum and I plot the velocity versus the position of the pendulum, this is the same circle. So circles in phase space, or tori, represent oscillatory behaviour. And this is an example of a structure, a mathematical structure of phase space. And what we want to kind of think about is how this structure changes. And this is in context of the structure-function relationship. There's also a third way of representing this, and this is to map it in parameter space. So, for example, if I have the external drive to the system, to the neural model, and the network balance, which might be the ratio of the inhibition versus excitation, I can say that in this red area here, the system oscillates, and in the non-red area, it doesn't oscillate it. And what we're interested in here is this boundary where it actually bifurcates. There's a phase transition, and the system changes state collectively. That's what we want to model as a seizure. So these are three different representations of the same dynamics of the same system. Now, normally bifurcation theory, you say that the system becomes unstable, there are positive eigenvalues, but I think we can go a little bit further by abstracting a little bit. So by abstracting, we can be a bit more precise. And I don't think it's necessary to actually completely get this definition. It's more to show you that you can be intuitive about how the mathematical structure of a system changes and think about a problem like epilepsy in this way. So I just want to introduce very briefly the idea of topological inequivalence. So when you've got a function, for example, y equals x squared, you know that if you feed in any number, negative or positive, you get a positive number. So here's the input of the function, and here's the output of the function, right? And if you had every element in the input mapping onto and one-to-one with every element of the output, it's called topologically equivalent. What happens is that if you're a topologist, for example, and you view the world as this, so just in this qualitative, geometric way, you wouldn't be able to distinguish between a coffee cup and a donut, because these map one-to-one and onto. But this is not the case with the bifurcation. So a more intuitive mathematical definition of the bifurcation is that the system is no longer topologically equivalent to itself. So in these models, they're deterministic. So the current state is determined by the previous state, and this maps smoothly. But at the bifurcation point, this mapping breaks down, where the system is no longer topologically equivalent to itself. I just wanted, again, to mention this structure-function relationship, because you're looking at the change in mathematical structure and you're seeing it that way. So Steve Schiff's going to be talking next about group theory, and this is also going to be about techniques that exploit mathematical structure, where you've got symmetries that are invariant under transformations. So these bifurcations can be local, i.e. a certain neighbourhood of phase space, or they can be non-local and occupy large areas of phase space. And we don't typically explore these using mathematical simulations. We use a technique called numerical continuation, which I won't go into now. So how do we then transpose this somewhat abstract concept onto the idea of a transition to seizure? So this is actually two pictures overlaid. So we'll start with the EEG traits in light blue of a complex partial seizure developing. And then we'll look at this one parameter bifurcation diagram that's drawn over the top. So at some point here, there's this phase transition where the system is no longer topologically equivalent to itself. And these two branches of the bifurcation represent the minimum and the maximum of the amplitude signals. So we can then map this to phase space. So this is a beautiful picture from Piotr Safinsky's PhD thesis, where the state variables are the excitatory activity versus the inhibitory activity. So first we can map the normal activity. It's actually just a dot once you take out the noise. It's just a straight line. So this is a dot, and the little squiggles around it are the noise, in fact. And then we can look at what happens when you have a transition or a bifurcation. There's this boundary that's crossed here, and then you go towards the oscillatory or the seizure-like activity, which is this large circle, again a donut or a torus there. So you can see that we can represent this change in mathematical structure of the system, and that's how we conceptualise the idea of a seizure transition. But this is only one candidate mechanism. There are other candidate mechanisms that also use bifurcation theory, for example, multi-stability and intermittency, which I won't be talking about today, just to give you an idea. So which parameter changes here to get this bifurcation is an interesting question when you're modelling epilepsy, because insight into the parameters that change that give these transitions give us insights into the physiological mechanisms, and this is how we can use this to develop new therapies and possibly in seizure prediction too. So certain parameters could be the external drive, the input, for example, the subcortical input. The network balance, of course, is a big one in epilepsy. The synaptic gains, which is essentially the network connectivities. The ionic dynamics, so Steve Schiff actually did a beautiful paper a couple of years ago where he measured the reversal potentials and showed that these change during seizure initiation and seizure termination. And connected to the homeostatic mechanisms that influence the ionic dynamics, this idea of endogenous regulatory mechanisms. I think this concept for me isn't addressed enough in modelling, and I really like this idea, and I'll come back to that, of these mechanisms within the brain that actually control the hyperexcitable behaviour of seizures that fail when you do get a seizure. So just as an example of the output of this is John Terry's group analysing the Wendling model. You can see this is the model outputs for various EEG traces, time series, and this is the clinical correlates. So you can reproduce the spike wave morphologies quite well, and this is done by actually changing the inhibitory population, synaptic gain on them. So you get polyspike complexes, etc. And this is using bifurcations, and in particular an interesting concept of false bifurcations or inflection points. So now I just want to briefly talk about some of the research we've been doing in Melbourne on the influence of synaptic mechanisms on these models and the transition to seizure. So the overwhelming majority of a lot of these models of epilepsy use current-based synapses. There are a couple of exceptions. Stravinsky's work, and then there is some in neural field theory, for example, the Liley model, Renium synapses, but the majority use current-based synapses. And when we model the synapse, we're really modelling the synaptic current coming into an equation. So a current-based synapse actually just linearly sums up the incoming current. So this is B, the population. This could be excitatory, inhibitory, or external. Now, there's no such thing as a current-based synapses. There are only conductance-based synapses in the brain. This is an approximation, and I guess we're having a look to see if this is okay and comparing it to conductance-based synapses. Now, in conductance-based synapses, which we find in more of the spiking models, it's a different mechanism. We have the conductance, and then it's multiplied by feedback from the state variable, the membrane potential, the difference here. So it's multiplicative and it's non-linear. And this is the difference between them. So I guess what we're asking is if we model seizure dynamics using this class of models, and then we modify them so that they're more biophysically accurate, how does this change the results? So this is quite theoretical research. As I said, I'm not using any data. I'm just examining the current models that have been used and having a look at what they could mean physiologically. So the aim of this research is to change the synaptic mechanism and then examine the effect on the transition to seizure or the bifurcation structure of the model. And again, these insights into how the different parameters change can give us insights into physiological mechanisms. Can we identify any regulatory mechanisms from this? And what are these important parameters during seizure initiation and termination? So again, this is the drive of this is to get models to sharpen the questions, to tell experimentalists where to look, and then start this iterative procedure back between the theory and the experiment. So the neural model we use is like the one I showed before, where you've got a first order coupled equation, and we use this one because we use this form so we can distinguish between the synaptic currents where we can model the mechanisms separately. So this is the membrane potential, this is the lead current. We have an output equation, which is just spatially uniform or isotropic and homogeneous cortical sheet, and then we have a typical signal equation coupling the two. And what we do is we use another abstract idea called a homotopic mapping. So before, when I introduced this idea of topological equivalence, this is a slightly less strict mapping. So anything that's topologically equivalent is also homotopic. I'll explain what that means in a minute, but the converse of this statement isn't true. The homotopy just requires a continuous mapping. So an example of this would be if I have a sphere and I shrink this sphere to a point by letting the radius go to 0. This mapping is still continuous between the two, but they're certainly not one-to-one. And we do this so we can build a model that encapsulates both of these mechanisms and then change one mechanism to the other and watch what happens to the dynamics. So an example of a homotopy is this linear mapping here. So our homotopic parameter is this kappa function here. We vary kappa between 0 and 1. So you can see that when kappa equals 0, this term disappears, and we have the function fx. And then as we change kappa from 0 to 1, this term disappears, and we have g of x. So what we're doing is mapping fx to g of x continuously. And we can express our synaptic current now as a homotopic mapping. So here we have the conductance, which we model just as a decaying exponential, the same as the current, and this is the incoming firing rate. And we introduce this new variable, which is the mean membrane potential. So this is a static parameter. And this term here, the homotopic parameter is in front of, is really the fluctuations of the membrane potential around the mean. So you'll see, for example, when kappa is 1, then these two V bars cancel out and you get your V minus E times G, which is Ohm's law. It's just your typical conductance-based equations. But when kappa equals 0, then this term disappears and this goes to a constant, and this is just a linear sum, which is your current-based model. So we want to deform this model to the other one. So again, the current base is linear and additive, and the conductance base is nonlinear and multiplicative. Now we can reformulate this in an analytic framework, and possibly a more physiologically intuitive way, by reformulating it as a differential operator. It's not linear, because we've redefined this time constant now. So the membrane time constant now is inversely proportional to the input. It changes with time. So when you crank up the external drive, for example, here, the time constant shrinks, it's dynamical. And as you decrease it, the time constant increases. So we're going to cut straight to the bifurcation analysis of this model now. This shows what happens when you change the homotopy constant. So this is conductance base and this is current base. It goes to a static constant. So this process here is basically representative of the leakiness of the membrane potential, that feedback term from the conductance base model. So cutting straight to the bifurcation diagram, which I kind of showed before, you've got the external input and the network balance. And you can show that for a region here, you get a transition or a bifurcation into oscillator activity. But for the same conductance-based model, you don't find this at all. So why is this interesting? Because this seizure behaviour, or this transition, has been suppressed by a kind of regulatory mechanism, if you like, at a synaptic level. And what we want to do now is do a homotopy, our mapping, from this diagram to this diagram, from the oscillatory version, where the external drive pumps it into an excitable state, to this version where you pump up the external drive and nothing happens, it remains stable still. So what we do is we can show in the fixed points, at a critical point of the homotopy parameter, plotted against the fixed points, the stability changes. You get a qualitative change in the system. This also is shown in the eigenvalues, and it's also shown on the argand plane as well, where two pairs cross. So what that means is this critical point shows that the feedback at some point from the conductance-based synapses overrides the excitability of the system, even when there's an increasing external drive. So just to summarise quickly this area, this section, current-based synapses are linear and additive. They've got a fixed membrane time constant, and they get excited and you have a state transition when you increase the external input. Conductance-based synapses are non-linear and multiplicative. They have a time-dependent constant, and when you crank up the external input, nothing happens because the synapses act as a regulatory control mechanisms. So we can kind of interpret the homotopic parameter, which took us from one synaptic mechanism to the other. That V minus V bar term is really the fluctuations around the membrane potential, and this is really representative of the synaptic background activity, the random fluctuations of such a large recurrent network. And if you were to treat this stochastically, it really represents the second moment, or the variance of the membrane potential. So nearly all of the models previously use current-based synapses. And when we make the synapses more realistic, we find that we get qualitatively different results. And what this means for epilepsy is that if we have large fluctuations, for example, seizure-like behaviour, where you get these spikes, then this is going to show up in the feedback from the fluctuations around the membrane potential, and this is why we get qualitatively different results, this idea of a regulatory mechanism. So the point here is that how you model the synapse is quite vital to understanding epileptic dynamics in these models. In a way, I think the way you model the synapse is more important than the way you model a neuron, because at the synapse, so much happens. There's synaptic connectivity between white and grey matter, there's neuromodulation, neurotransmission happens, drug efficacy and action. And I just want to have a quick word about regulatory mechanisms. So there are multiple regulatory mechanisms on multiple scales. So the first one is at the network level. In the network structure, we have this idea of feedback, feed-forward and surround inhibition. This can be non-local, for example. intrahemispheric compared to, intrahemispheric compared to non-local, which is interhemispheric compared to even subcortical from the thalamus. Then you have it happening at the synaptic level from the multiplicative feedback, which I just showed, and then you also have it happening at the ionic level, where you get homeostatic mechanisms, glial buffering, diffusion, etc. And one of the questions of this kind of modelling, for me really, incites, is I find it utterly amazing that all of these dynamic or compensatory overlapping regulatory mechanisms which control hyperexcitable behaviour all fail simultaneously on multiple scales when somebody has a seizure. I think that's a really interesting question. I'd like to pose that. How can we enhance these regulatory mechanisms to prevent ictogenesis, for example, by exogenous means? And now I'd just like to finish that section and sum up. So we make many assumptions when we make neural models, anatomical, physiological, mathematical assumptions. It's really important to understand these assumptions, which ones are justifiable, which ones are conjectures, what the limitations of the model are, when they break down, when we take them outside of their operating regime. And of course, different models use different assumptions to model different phenomena. A neural math model, again, has no spatial structure compared to a neural field model. And you see the two. And I just want to remind you of that structure-function relationship on two different layers. So when we conceptualise epilepsy, we think about how the mathematical structure of a system changes, and we kind of have a thought experiment. And this could be really conceptually insightful, particularly in some of the physiological mechanisms that may be behind ictogenesis. And getting a good grip on this and how the parameters relate to the system can really help us to design novel therapies and tell experiments where to look and where to do the next experiment. Again, the point of these models, as Bill described, is to reproduce and describe experimental data. And most of these models are still in a descriptive state, and we'd really like to get them into a predictive state, like the Hodgkin-Huxley equations. And this top-down approach, the Reformulate approach, can work. The Hodgkin-Huxley equations is really just curve-fitting, as is the Schrödinger equation in quantum mechanics, which is probably the most successful theory used to predict experiments, something like 15 decimal places. We didn't know all the information when we devised these theories. We only had a rough outline. So it shows this experiment has hope and potential. And the second goal that I discussed is to develop these methods. We're still in progress, really, of developing these models to accurately describe brain dynamics. As I said, it's a very complicated interacting system, so we're still learning about how to mathematically describe these. So we want to develop these models that are more appropriate for epilepsy and really target what we're doing. And my work that I presented here today, what we're doing at Melbourne Uni, is an example of just refining and developing these theoretical methods. So the big question is what features to leave in and out of these models as we ascend scales. This should constantly be always checked and tested, relating to spiking models and, of course, experimental data. So modelling can give us insight into physiological mechanisms behind epilepsy, and then this can help us to utilise this understanding of relationships to predict seizures and develop novel therapies. Current and future directions, I guess we could treat these as further discussion points, is to treat the noise in the system properly, meaning stochastically. Another point is to include more detailed network dynamics and to add ionic dynamics into the system. So Piotr will be talking about this in his keynote lecture. Again, identifying regulatory mechanisms, I think this is a really underdeveloped side of neural modelling that I think would be potentially very clinically useful. And then data-driven modelling, actually doing proper parameter estimations of models. So Dean Freestone will be talking about this later as well. So I think if we can get agreement between the mathematical and the computational and the experimental, then this will yield quite meaningful results that are not only rigorous but clinically relevant. So I just want to end by quoting something amusing by the great Nikola Tesla, which I often remind myself of when I'm thinking about very abstract mathematics, and that is that one must be sane to think clearly, but one can think quite deeply and be quite insane. And I'd like to acknowledge the Department of Medicine and Electrical Engineering at the University of Melbourne. Thanks.
We've got time for questions. John?
Great. So I noticed you mentioned a little bit about regulatory mechanisms. Which we brushed over that fairly quickly. Because in most of the models we do that, we ignore regulatory mechanisms.
That's right.
But it often occurs to me that when we're trying to predict seizures, perhaps it's those regulatory mechanisms that might explain why we get so many false positives, i.e. we actually did predict that a seizure was going to occur and the brain was on a path to seizure, yet the regulatory mechanisms kicked in and stopped it. So I wonder if you have any thoughts on how we might overcome that hurdle, because otherwise it strikes me that many of the sort of seizure prediction algorithms we create might be doomed to failure because we aren't accounting for it.
Yeah, I guess one of the ways is to perhaps look at this idea of near marginal stability or criticality of the brain. We were producing a lot of endogenous oscillations, and only some of them become unstable and turn into seizures. And this, I guess I'll relate this to the network structure, for example. You might have unstable network structures that propensate more unstable behaviour. So a way of possibly including this into the model would be, say, from ionic dynamics. I know there's been some people that have done some work on how to terminate seizures by increasing transporters between ions, for example. It'd be one role, and then to experimentally test this. But I think you're right. I mean, what constitutes a person to go into this critical state where they have a seizure? It's obviously the failure of multiple things, because some things can be corrected by these regulatory mechanisms, as you say, on multiple levels. So how many of them do you have to have, and what type, to pass this threshold where the actual seizure it becomes, you get ictogenic behaviour and actually passes this? So I think that's an interesting question.
I guess as well it comes down to how detailed a description you need to give to those mechanisms. Can you actually lump them all together, as you might do with some of these clean field models? Do you need to unpack them to individual contributions? I
think they're on different scales, and again this relates back to the problem of linking the scales. So for example, you might have a malfunctioning KCC2 transporter, and that could depolarize the reverse potentials, causing suicidal behaviour. At the same time, you might have cell death in one of the foci, where you get a network imbalance. And you've got different regulatory mechanisms compensating for this, but there's a real overlap, even though they're on different scales. So it is difficult, and I think it again broaches that problem of how we link the behaviour on different scales. You've got this top-down feedback, and you've also got bottom-up feedback as well.
Any other questions? Yep, Piotr.
Piotr?
I was wondering, is it possible to somehow to distinguish between pathological oscillations, like limit cycles, and healthy limit cycles in your model? Because, of course, there are also oscillations that carry towards healthy cycles. So, is it possible to distinguish these two?
Yeah, I think that's a really good question. I mean, obviously, the alpha rhythm, for example, is an oscillation that's very healthy, and that's also been described by hot bifurcation in quite a few models. I guess I didn't really look at relating it to that kind of experimental data yet. My idea was to have a proof of concept, so that if we use this family and this class of models, and we use this synapse, and if we make the synapse more biophysical realistic, then we get quite different results. So we need to take a look at, how we're modelling the synapse and if that's important. But I think that would be great to do, and I think an example might be you might be able to distinguish, for example, a limit cycle or a hot bifurcation from a homoclinic bifurcation. But it's very difficult to extract out the endogenous ones and the pathological ones. This is not an easy thing to distinguish, particularly in a patch of cortex as well. So if you're modelling a large area, I guess you can look at the epileptiform behaviour, and this comes from the multiple populations and time delays, but then the complexity of the model increases so much it's then difficult to tease apart. And also the problem of rhythmogenesis in neural field models too is a pretty open question of how these endogenous oscillations are generated. Even alpha rhythm is still quite a large mystery. Yeah. Okay, thanks.
All right, Andre. Our next speaker is Steve Schiff from